This is the final thing we will consider in gravitational fields, mutual orbits. Do check with your specification whether this is included. It is included in WJEC. Even if it's not included in your specification, it might well be worth having a look at it, because it's the kind of thing maybe for an AA star question, they could just say, here is something that you haven't considered that's not on the specification, and you have to deal with it. So this may be on your spec, or it may be a stretch and challenge, but I do think it's worth considering. Okay, what is a mutual orbit? Well, we could talk about binary star systems, but basically wherever you have an object orbiting something else, whether it's the moon around a planet, or a satellite around a planet, or a planet around a star, then we have a mutual orbit. Because normally we assume that the large object in the middle isn't moving, but it does actually move a little bit. And they have a combined center of mass. Now, normally the center of mass will be within the larger mass, and that's what defines a planet. So if we think about Pluto, which very sadly is no longer considered to be a planet, there are various reasons for that, but one of the reasons is this center of mass between its moon Charon and Pluto is outside of Pluto. So the moon is actually pretty big compared to Pluto itself. So we actually get quite a noticeable mutual orbit. So Pluto will be orbiting a common point. Generally speaking, when we're looking at stars, then this wobble is very insignificant. However, it's really useful, and we might look at this later on in the course when we talk about stars and the universe. So star wobble is something that we can look at through telescopes, and we can use that information to identify the number and the size and the distance of the planets orbiting that star. So this is very much a useful thing in astronomy. So what can we say about these mutual orbits? So as we know already with gravitational force of attraction, these forces will be equal and opposite, Newton's third law. It should be fairly intuitive that the larger mass will have the smaller orbit and will move more slowly because it's got a larger mass, but they both have the same time period. That's really important. Right, we have various formula here which we need to consider. We're not expected to derive these, fortunately. You can look into that if you want to, but we're not going to do that in this video. So we've got, before we look at the formula, let's identify what all these symbols mean. So we have M1, which I've called the smaller mass with a larger radius, and M2 is the larger mass with a smaller radius. R2 is associated with M2, and R1 is associated with M1. So we have a center of mass. So this case here could be Pluto and its moon, or it could be a binary star system, where both of these objects are orbiting a common center of mass, which is outside of the larger mass object. D is the distance between the two centers. So if we have a look at this one here, we've got R1 is equal to M2 over M1 plus M2 multiplied by D. R2 is the same idea, but we've kind of swapped these values over. D is still on the top, but now M1 is on the top, but the total mass M2 plus M1 is on the bottom. And then the time period, which will be the same for both of these masses, is given by this expression here. You should see a similarity here with Kepler's third law. Obviously it's different, but there is a relationship between Kepler's third law. So let's have a look at a calculation, and hopefully that will give you a better understanding. So we're going to look at Pluto and its moon. So we're going to find the orbital radius first of all, and then we're going to calculate the orbital time period. So we're given big G, we're given the mass of Charon and Pluto, and the separation. Remember, that's between the two centers of mass. So first of all, we could call Pluto M1 or M2. In this case, I've called that M1. So we're going to find R1. So we're going to have M2. So it's the other mass, it's the smaller mass, it's the mass of Charon, which should make sense because the radius should be larger. So we'd expect to have the smaller mass on top. We're going to multiply, we're going to leave this in kilometers, so multiplied by D, 19,600, divided by the total mass, and we get our value here, 2,120. And then if we're trying to find the orbital radius of the moon, it's going to be, We could do the same calculation but with the other formula. That's absolutely fine, but it's probably easier because we know the total distance and we know the radius of 1, and the total distance is the sum of the two radii. It's probably easier just to subtract our previous value from D. So 19,600, take away our first answer, and we get 17,500. So that should make sense because R2 would be larger because that's further out, that's the smaller mass. Okay, so if you want to check, you could use this other formula here, but you should get the same value. And then part C, or part B rather, we're trying to find the orbital time period. So this should be a straightforward substitution. So 2 pi is on its own. We're going to find the square root of d cubed. Remember, this is kilometers. So we're going to have this in meters. So 19,600 multiplied by 1,000, and then all cubed, then divided by g, and we just add together the two masses, and we get our answer in seconds. So depending, that's probably fine for this question, but we might be asked to write that in hours or days, so we could convert that as required.